So before we start the first lecture, let me introduce to you our first speaker. So we start our lecture on algebraic graph theory with the first mini course, which will be given by Štefan Gyürki, and he has received his PhD from Comenius University in Bratislava, Slovakia, in 2009, and then he spent 1 year as postdoc student at Ben-Gurion University in Israel. And actually, as Štefan said, twice he visited Akademgorodok in 2016 and 2018 with giving wonderful talks at the conferences on graphs and groups. And currently he works at the Slovak University of Technology as researcher. What we can say about his main interests, they are in algebraic graph theory and algebraic combinatorics. And his main research topics include, but not restricted by, directed strongly regular graphs, computation methods in computer algebra, gap, and congruent configuration and association scheme, more precisely Schurian and non-Schurian association scheme. So the last topic is exactly included in his mini course, which gives a not so short introduction into algebraic graph theory. So I'm really happy to announce that the first lecture of this lectorium will be given by Štefan Gyürki, who is our friend. So the first lecture is coming.
Thank you very much, Ilona, for a very nice and kind introduction. And also I feel honored to have this opportunity to talk to students all around the world. I have to say at the very beginning that my talks will be oriented on students. So probably those who are already experts in algebraic graph theory, probably they will hear nothing new at least in the first few lectures. So really I would like to focus on students, and the chosen level is somewhere in between the undergraduate course and PhD course on algebra. So it will be necessary to have basic knowledge on algebra, but all other kinds of things will be at least somehow mentioned or defined and so on. So I will give the basics for everything I would like to talk about. Okay, so my first topic is permutation groups, and I have chosen this because in algebraic graph theory, as you can deduce from the name, some kind of graph theory meets with algebra, and one of the natural meeting points is exactly permutation groups, because groups are very central objects in algebra, and you can think about a graph when you are examining its group of automorphisms, and exactly a group of automorphisms of a graph can be regarded as permutation groups. So I will talk today just about permutation groups and some of their relations. Okay, so I'm sorry, I have some, okay, now it works. So as I was mentioned, that graphs can be examined using groups or automorphism groups, and on the other hand, we know that each group can be realized as an as a full automorphism group of graph. This is, I think, Frucht's theorem. So this is also basic information from graph theory. And moreover, each abstract group can be realized as a permutation group. This is the well-known Cayley theorem from abstract algebra. So really, permutation groups provide a natural meeting point of algebra and graph theory. So just to repeat some basic definitions, under permutation on set omega, we mean a bijection that is a one-to-one mapping of the set onto itself. I will refer to this set omega sometimes as a ground set, because when we will talk about different stuff, then there will be a lot of sets we can refer to. So under the ground set, I will mean the set on which a permutation is acting, or a permutation group. If I have a permutation G, then the image of an element from the ground set will be denoted as alpha and superscript G. We will see later on why this notation is suitable for our situation. Also, from basic course of algebra, you can know that the set of all permutation forms a group because it is closed under inverses. The identity permutation is there, and the composition of permutation is also a permutation. So really, it is easy to check that this is really true. And if you take ground set omega and you will create all the permutations on this set, then you obtain a group which is called usually the symmetric group, and it will be denoted as sim omega. Those who are reading blogs on the internet concerning mathematics, you can find also a blog which is called Sim Omega, and now you can understand why the name of that blog, the name of that blog was chosen. And after that, naturally, you can ask the question that what kind of groups this symmetric group has. And the subgroups are just subsets which are satisfying the three axioms of a group. And in the situation when we have a group G acting on or having permutations which are permuting symbols or elements of the set omega, then we say that the group G acts on the set omega. A natural way to display permutation groups is that the elements of the ground set omega will be the numbers, the natural numbers 1, 2, up to n, but this is not necessary. For example, if you have vertices of graphs and their permutation, then you can have permutation or permutation group which permutes the labels of your vertices. We will use abbreviation SN for the symmetric group acting on the symbols 1, 2, up to n. Again, if you take all the permutations of an n-element set, then you probably even from the high school can know that the number of all permutation is n factorial. if we will talk about groups, then usually we assign at least two numbers to the group, its order and its degree. By degree of a permutation group, we will mean the number of elements from the ground set. So on how many elements the group acts on. Here I need to notice that since in the group theory, degree is reserved, the notion of degree is reserved for this term, then the term degree from graph theory, here we will use as valency of a graph. So just to avoid some confusion. But if we will come to some example where there will be also degree of graph, then I will again, I think, notice you that I mean valency under the name degree, or whether I am using a degree of permutation groups. So as I mentioned, natural action of a group when we are regarding graphs is the action on the set of vertices. So if one would like to investigate the full group of automorphisms of a graph, then in fact he is finding permutations from the symmetric group of the vertex set. So the automorphism group is a very natural permutation group. So if you have, for example, the symmetric group on 3 elements, then you can create 6 permutations. By E, I mean the identity. And here I am using for displaying permutation the cycle notation, moreover the reduced cycle notation. For example, here this element fixes the element 3 from the ground set, and since it forms one cycle, it is not displayed. So I will sometimes talk about cycle representation of permutations, or reduced cycle representation where the one cycles will be omitted. If one would like to find all the subgroups of this concrete symmetric group of degree 3, then if he will approach this problem in naive manner, then he can consider all the combination of 6 elements, whether they form a group. But of course, in more intelligent way, you can simply just put the identity into that subgroup, because identity has to be an element of the subgroup. After that, also you can put into one package these 2 permutations, because they are inverse one to other. So in fact, in a little bit more intelligent manner, we don't need to check 64 subsets, but just 2 to the 4th power. And we can easily obtain, in this case, that the symmetric group of degree 3 has precisely 6 subgroups. And these are displayed here. If you will go further, then it is much harder to find all the subgroups of S4 or S5 and so on, because the number of elements simply grows by factorial. Now, another basic notion is the product of permutations. And here we will see why I'm using the notation for the image in this form. So probably all of you know how to compose two permutations or how to create product of two permutations. So we just have to say which permutation will be applied first, because this is the usual composition of functions also. And here in this notation, I am using that first the permutation G is applied, and after that the second permutation G, and that's the way how I am obtaining the permutations, the product of these two permutations. So first I am applying G to X. I am obtaining the image of X under this permutation, and that image, on that image I will apply the permutation H. So in order to see this in example, a very easy example, for example, if I have permutation G and H as displayed, then I will obtain the image of the element 1 under the composition in the way that first I am applying G to 1, so G sends 1 to 2, and after that H sends 2 back to 1, so the image of 1 is 1 under the composition of this permutation. This creates for me this cycle of length 1. After that, I can, in the same manner, consider the element 2. 2 is mapped to 3 by the permutation G, and 3 is sent further to the element 5 in the second permutation. So that means that 2 is sent to 5. And if I will play this game further and further, I will obtain that the product of these two permutations is a permutation which fixes the element 1 and permutes cyclically elements 2, 5, 3, and 4 in this order. Okay. We can define for a group system which we can select some elements of the group in such manner that each element of the group can be written as a product of the elements or their inverses from this set. So it doesn't matter how many times I am using a single element or its inverse. The important thing is that each group element can be written in some way as a product of the elements from the generating system or their inverses. So these elements from the basic set will be, from the generating set, will be called generators, and we say that the group is generated by this set, and we write either in this manner that in brackets S, or we just simply write the list of the elements which generates the group G. At any moment, you are welcome to put some question, or if something is clear, non-clear, or anything you can ask during the lecture. I don't want that somebody will miss some of the concepts, so you are welcome to interrupt me if in suitable manner and place. Okay. Now, there are very special permutations which are called transpositions. These permutations just interchanges two elements of the ground set. That means that their cycle representation contains just one cycle of length 2 and all the other cycles are of length 1. So this is the simplest permutations we can have. So just interchanging two elements. But we have to be careful because if we write, for example, just transposition of elements 3 and 5, then from this it is not clear in which group we are working. So if it is clear from the context, then we can afford this notation, but in all other cases we have to say that we have a permutation from S5 or from S6, and after that we can make this simplification. And transpositions play a very important role from another point of view also, because we can obtain the symmetric group as products of transpositions. So the following proposition says that one can obtain the symmetric group Sn, for example, as the set of all transpositions in Sn as generators. That means that I can pick any element of the symmetric group and I am able to write it as a product of transposition. And the key fact for the proof is that if I have a cycle, then any cycle can be written as a product of transposition in this manner. And in the next step, each permutation can be written as a product of disjoint cycles. So from these two pieces, I can obtain that I can generate the symmetric group purely from the set of all transpositions. Now, but we can take also some subsets of the transpositions. For example, in the second case, it is enough to choose transposition which interchanges consecutive elements of the basic set. This works for a very similar reason, because if I have a transposition Ij, then this transposition can be written as a product of these transpositions. So just using these transpositions which are interchanging consecutive elements, I can obtain any transposition Ij, and now further I can apply the same proof as in the first step, that if I have the collection of all transposition, then I can obtain each permutation from the symmetric group. And similarly work the third and the fourth set. If I have the transposition just 1, 2, 1, 3, and so on, then I can obtain any transposition Ij simply as product of 3 transposition of this type. And again, I am coming to the end that if I can obtain each transposition, then I can obtain each permutation from the symmetric group. And in the fourth item, we have a single transposition and a cycle of length n. Again, just by using these two permutations, I can obtain in first step all transpositions which interchanges two consecutive elements, and after that I can continue as in the step 2. So here we can see at least 4 sets of permutation which generates the full symmetric group of degree n. On the other hand, it is interesting to play with transposition because we can see more and more properties of permutations. In first step, we can notice that the same permutation can be written in many ways as product of transposition. But it is not hard to prove that in all these products, the number of transpositions have the same parity. And as a consequence, it gives sense to define so-called even or odd permutations just according to the number of transpositions in the product. And the name was chosen correspondingly with the parity of numbers, because all the properties will be the same. So from the cycle representation, it is easy to see that the permutation is even if and only if the number of cycles of even length in the cycle representation is even. Again, the proof is on the level of, I will say, high school, that it's playing simply just with the parities of the permutations and numbers. And also the following lemma that two permutations are, the product of two permutations is even if and only if both have the same parity. So both are either even or odd. And it is clear that the identity permutation is even, and thus we can consider the set of all even permutation, and based on the previous knowledge, we can see that the set of all even permutations forms a group because the identity is there. The product of two even permutations is even permutation, and if we have a permutation, then its inverse is also even if the original was even. So this is the so-called alternating group, and it is an easy counting argument which says that the number of all even permutation in the symmetry group n is n factorial divided by 2. So precisely half of the permutations are even and half are odd in the symmetry group. So we can see the alternating group of degree 4 here. We have just a few types of permutations. Here we have 2 cycles of length 2, or 1 cycle is of length 1 or 2, 3, and the identity. So this is how the alternating group on 4 elements looks like. And we could see also that the number of that subgroup, number of elements in the alternating group divides the order of the symmetric group, and this is basic information again from abstract algebra that the order of any subgroup divides the order of the overgroup in finite case. Moreover, this quotient is equal to the number of cosets of the subgroup in the overgroup. So, for example, if we already seen the symmetric group of degree 3, if we go further, then we have the symmetric group of degree 4, which has 24 elements, and 24 is quite big number for just considering the number of divisors and possible orders for the subgroups. But if we will take time and play a bit with this group, we can find that for each possible order of a subgroup, we can find at least one subgroup of that order. And if we will do a complete search, then we will find 30 different subgroups of the symmetric group of order 24, that is degree 4. So we can have a feeling that if a number divides the order of an overgroup, then it will be an order of a subgroup. But the converse is not true, or this is not true, because, for example, 6 is a divisor of 12, and the alternating group A4, which has order 12, doesn't have any subgroup of order 6. In order to prove this, we will need another basic notion, which is orbit of permutation group. If we have a permutation group, it is quite natural to define a relation, a binary relation on the ground set omega, in such manner that we will say that alpha and beta are in the relation R if and only if alpha can be mapped to beta by some element of the group G. It is quite immediate to see that this relation is an equivalence relation, because the identity permutation sends alpha to alpha for each alpha. That means that it is reflexive. Also, if I can map alpha to beta, then there exists some element of the group which does this job. And the inverse permutation to this permutation sends back beta to alpha. So if alpha beta are in a relation, then beta and alpha will be also in the relation. And by the properties of the composition of permutation, one can see that this relation is also transitive. Now, so we have some natural equivalence relation on the ground set, and the equivalence classes of these relations are called the orbits of the permutation group G omega. Another usual way how to define the orbits is that pick an element alpha and create the set of all images of this element, and you will obtain the orbit which contains alpha. And if you will do this with all the elements or all the elements from the ground set, then you will obtain all the orbits of the group. Now, we can also define the length of an orbit simply as the number of elements in the orbit. And there are some special permutation groups, and a very important class of permutation group the so-called transitive groups, and these are precisely those who has just one orbit on the ground set. Otherwise, we say that a permutation group is intransitive, that is, it has at least 2 orbits on the basic set. Here I show you a very interesting example that, for example, the group G, which I generate by this one element, clearly has 3 orbits, because one can be mapped to 2 and 3, 4 just to 5, and 6 forms a single orbit. So this group has 3 orbits, and their respective lengths are 3, 2, and 1. So this group is intransitive on the set 1, 2, 3, 4, 5, 6. Now take another group H, which is generated by a 6 cycle. Clearly this has just a single orbit. Therefore it is transitive on the same set. Now, if we think about these 2 groups on abstract level, then it is easy to see that both groups G and H are cyclic, because they are generated by a single element. And also it is easy to see that the order of both groups is 6. So G and H are isomorphic as abstract groups to the cyclic group of order 6. But G is a permutation group which is intransitive, and H is a transitive permutation group. So we have to be careful when we are talking about an action of a group, because if we are not giving precise information, then it can lead to confusion. So just to say that the cyclic group of order 6 is transitive or intransitive without any specification or more information is senseless. So, of course, if some knows the context, then he can afford this. But without giving precise information, we cannot say that a group is transitive or intransitive. So this is, I would say, one important difference between abstract groups and permutation groups, that groups which are isomorphic on abstract level, they are not necessarily isomorphic as permutation groups, or even they do not need to be very similar. Okay, so this was an important remark. Now let's move on. With orbits also, they are coming subgroups of permutation groups which are called stabilizers. Stabilizer of an element of basic set or ground set is the set of all group elements which fixes alpha or the chosen element. And it is not hard to prove that this set of permutations forms a subgroup of G. And usually we write that the stabilizer of alpha in G as a group G and subscript alpha. But again, it can lead sometimes to maybe confusion, but that needs, again, precise information or description of everything. So if I am writing, for example, the stabilizer of element 1 in A4, then I mean these three even permutations, identity 2, 3, 4 and 2, 4, 3. So we can see that all these permutations leave the element 1 on its place. And why I mentioned that orbits are in close relation with the stabilizers, it will be clear after we will see the orbit stabilizer lemma. If I have a permutation group G on the G omega, then the length of the orbit of any element alpha is the number of cosets in G of the stabilizer of this element. So one can obtain the number of groups as a product of the length of orbits of any element and multiplied by the order of the stabilizer of this element. So it is easy to see that it's just a special case of the Lagrange theorem, but if we take like this lemma, then we can read that the length of any orbit is also a divisor of the order of the original group. So this is a very valuable remark or knowledge, and a lot of useful or beautiful things can be done just using this information on group theoretic level. So I think I'm a little bit pushed by time, so I will just say a few words of the proof. The proof is related with the right coset decomposition according to this stabilizer G alpha. So here H is the G alpha, and the proof consists of two steps. That first, we can easily see that all these elements alpha to identity, alpha to G2, alpha to G3, and so on, are elements of the orbit of alpha under G. I'm not saying at this moment that these elements are different. But if we will prove that these all are different, then we will have exactly k elements, and it will prove that the orbit contains at least k elements. On the other hand, just by playing with the permutations and their products and the properties of the cosets, one can prove that if an element is from the orbit of alpha, then it can be written exactly in this style. So, oh, I'm sorry for this. So the orbit of alpha looks like precisely this set. And it remains to show after that all these elements are different. Again, it's an exercise on the basic algebra level. Now we can come back to the proof that the alternating group of order 4 doesn't contain any subgroup of order 6. And since if there is such a subgroup, then the length of orbits of such a subgroup should be a divisor of 6. So it can be either 1, 2, or 3. Important is to notice that the length will be not 4, so therefore that subgroup will be definitely not transitive. Now, if we consider the case then that such a subgroup contains an orbit of length 1, then the 6 elements of A4, or not A4, but K, are in fact permuting only the remaining 3 elements. But there are just 3 even permutations on 3 elements, so this case is not possible. And similarly, if there is no orbit of length 1, then that means that 4 elements can be divided just into 2 orbits of length 2. For example, 1, 2, and 3, 4. But again, if you consider the number of even permutations under this restriction, then you obtain that you can create at most 2 even permutations. And therefore, you cannot have 6 elements in a subgroup. So this is a way how to prove that the alternating group of order of degree 4 doesn't have any subgroup of order 6. Now we briefly touched the notion of some difference of permutation groups. Then in permutation group there is a concept which is a strong similarity. And this means, maybe the definition is quite unfriendly, but it says the only thing that if I have 2 permutation groups which differ just by the labeling of elements, then we are saying that these 2 permutation groups are strongly similar. For example, if I have this group and this group, then to everybody is clear that they are in fact the same, in a sense that they are related, and one can obtain simply from group G the group H if he will relabel the element 2 to 3, 3 to 4, 4 to 2, and fixing 1 and 5. And this is exactly how these bijection in the definition works. So G and H are, of course, a isomorphic as abstract group, but also they have some special relation as permutation groups, because you can obtain one from other just by relabeling the elements of the ground set. On the other hand, not everything works like this. For example, here I am showing 2 permutation groups which are both isomorphic to Z2 cross Z2, but clearly you cannot find a relabeling of elements which will send one group to other, simply by the reason that if you will relabel this cycle of length 2, then or this permutation, you cannot obtain any of these elements, because this permutation has 2 fixed elements, and in the group V there is no such permutation which will fix precisely 2 elements. So U and V are isomorphic as an abstract group, but they are not strongly similar. And if we take a permutation group which is transitive, then for the stabilizer, it holds that the stabilizer, both of elements are isomorphic as groups, and not only isomorphic, but also strongly similar. This works also if you are not considering transitive group, but intransitive, but you are, in that case, you have to take elements alpha and beta from the same orbit. And a special case of transitive permutation groups appear when the stabilizer of any element is just the identity. And in that case, we are saying that the permutation group is regular. And the regular transitive or the regular permutation groups also plays quite an important role in algebraic graph theory. For example, if you know how to prove that a graph can be realized as a Cayley graph, then you exactly are using this knowledge that whether the full group of automorphisms contains a regular permutation group or not. So these two problems are equivalent. Now, some consequences if we have a regular permutation groups, then clearly the identity fixes every element, but no other element of such a permutation groups fix more element or any of them. And it is easy to see that to prove that if G fixes alpha, then of course it belongs to the stabilizer of alpha, and a regular group, regular permutation group by definition has just one element in the stabilizer, and this is the identity. And the second property of regular permutation groups, that the order of such a permutation group is with its degree. It follows simply by the orbit stabilizer lemma that the stabilizer has just one element, so G, the order of G is equal to 1 times the length of the orbit, and the length of the orbit is, in that case, is the number of elements in omega. Now we can move to higher level of transitivity. If you have a permutation group, then you can in fact define various actions derived from the original action on the set omega. For example, you can create ordered tuples or some subsets of omega and so on, and you can naturally extend your action to that kind of objects. For example, if you have two ordered k-tuples of pairwise different elements, then you can ask a simple question, whether you can map alpha 1 to beta 1, alpha 2 to beta 2, and alpha k to beta k by a single group element. And if you can do this in permutation group G, that for each such k-tuple, you can, each such pair of k-tuples, you can find a group element, then you say that the group is k-transitive. Of course, this is a natural extension, because if you restrict this definition to k equals 2, then you are obtaining the usual transitivity. I think the most simple example is the symmetric group of degree n. It is easy to see that you will find such an element in the symmetric group which sends an n-tuple to another n-tuple of different elements. And more interesting example is the affine general linear group over a finite field of prime order. If you have a finite field on p elements, then for each A and B, you can define a linear mapping or a mapping which to an element x of the finite field gives an image which is counted by A times x plus B. If A is non-zero, that this description defines really a bijection. And it is not hard to see that such mappings form a group. Now, since we are in a finite field, then we can consider the question whether if I am choosing two pairs of different elements, whether I can send the first order the pair to the second one. This means this question is equivalent to asking whether this system of equations has a solution in the finite field. And of course, if A is non-zero, then you can see that the system is regular and it will have a unique solution. And that means that you can send really each pair of different elements to each pair of different elements by some element of the group. This means that the group of affine linear transformations in this action is too transitive. Now, the next basic thing which is very useful in algebraic graph theory is the cycle index. And the cycle index is very easy to understand, but it provides a lot of information about combinatorial objects just by the knowledge of the cycle structure of the corresponding permutation group. So slowly we will come to that index. So similarly as with the groups, from also for the permutations, you can define similarity, and simply two permutations are similar if and only if they have the same cycle structure. That means that, for example, here permutation G1 and G2 are similar because both have two cycles of length 1, one cycle of length 3, and one cycle of length 5. And again, it is easy to see that this defines an equivalence relation among the permutations from the symmetric group. Very similar concept is conjugation. We say that two permutations G1 and G2 are conjugated in the group G if there is an element H in the group G such that H inverse G1 H gives you the second permutation. Again, this is also an equivalence relation, and equivalence classes are called conjugacy classes. Now, if you are working with the groups, with the symmetric group of degree n, then these two things coincide. The similarity and the conjugacy of permutations are the same. And we can see this just by simple counting arguments. If you have two permutations which have the same cycle structure, that is, they are similar, then in Sn you can find a permutation which is the following, that alpha 1 sends to alpha 1 prime, alpha k to alpha k prime, and so on. So this is clearly a permutation in Sn. And if you check what you will obtain in the H as a product H inverse times G times H, then you will realize that exactly in this manner you can obtain the second permutation. So if two permutations have the same cycle structure, then they are conjugated in the symmetric group. And oppositely, if two permutations are conjugated, then it is very easy to see that they are also sharing the same cycle structure. So, and this is usually the trick when you would like to relabel two permutations with the same cycle structure. That you simply take the permutation which sends you one label to other, and you do the conjugation. Now, the problem is that if you go to subgroups of the symmetric groups, then the similar proposition is not necessarily true, because, for example, if you take the permutations 1, 2, 3 and 1, 3, 2, they are clearly similar, and they both live in the alternating group A3. But if you will find the permutation F, which sends 1 to 1, 2 to 3, and which will do the, I will say, the job by conjugation, then you will see that this permutation is not an element of A3, that is not an even permutation. So these two permutations are conjugated in the symmetry group, but in the alternating group they are not conjugated, simply because the candidate for the conjugation escapes from that group. So also one has to be careful when he's talking about conjugation. You have to say where they are conjugated. So as we could see, the cycle structure is a very good notion, and from this reason it is sense to assign to each permutation its cycle type. Cycle type of a permutation is just a polynomial expression in some variables, when, for example, x1 to j1 says that permutation has j1 1 cycles, and x2 to j2 says that the permutation contains j2 cycles of length 2, and so on. And if we sum these expressions through all elements of the group, then we obtain the cycle index of the permutation groups. And of course, we do not have to forget to divide it by the number of elements of the group. So it is an arithmetic means of the cycle types. For example, the permutation group in its usual action has 6 elements. The cycle type of the identity is x1 to the 3rd power, because there are 3 cycles of length 1. The next 3 elements have cycle types x1, x2, because they contain 1 cycle of length 2 and 1 cycle of length 1. And there are also 2 elements which are 3 cycles, so they are contributing to the cycle index by elements x3 to the 1st power. And this means that the cycle index of the symmetry group of degree 3 is this expression. Okay, the next useful term is the character of a permutation, and here we are defining character of a permutation as the number of fixed points in the corresponding action on the basic set. And the knowledge of the characters help us to find the number of orbits of a group on the basic set omega. And this is what says the Burnside lemma, or also known as Cauchy-Frobenius-Burnside lemma, that the number of orbits of a permutation group is...
Stefan, it's too fast. It's too fast.
It's too fast. Okay. Where I have
Even
to...
for me.
Where I have to come back. Yes, I intended to finish in 1 hour, but this is not necessary.
Štefan, please take your time. Yeah.
Okay, so where I have to continue, which I didn't. So
Natalia, would you please point out which place you would like to start?
I think that for me it was very slow from this slide than Stefan demonstrating, but possible for somebody it was too fast some slides ago.
Okay, from which slides you think we need to start?
Okay, I think this place is a natural place for restarting the explanation. So to each permutation, I can introduce a polynomial expression which says that which says about the numbers of cycles of specified lengths. For example, J1 says how many one cycles the corresponding permutation G has. J2 says how many cycles of length 2 are contained in permutation G, and so on. So to each permutation G, I can assign a polynomial expression which is formed or created in this manner. And this is called the cycle type of the permutation G. Okay, I will skip this. I will come back to it later on. So, for example, if I am taking the permutation group S3, which acts on elements 1, 2, 3, then it has 6 elements. One element is the identity. It has 3 cycles of length 1. That means that the cycle type of this permutation is x1 to the 3rd power, because I have 3 cycles of length 1. And there is no cycle of length 2 and no cycle of length 3. So I can write x2 to the 0 or x3 to the 0, but they are giving me 1. So I am just forgetting this. Also, if I am considering the 2nd permutation in that group, then it has 1 cycle of length 1 and 1 cycle of length 2. That means that the obtained polynomial expression is x1 to the 1st power and x2 to the 1st power. That means x1, x2. Similarly, for the next 2 permutations, I am obtaining x1, x2 as the cycle type of the permutation. Now, there are 2 more elements in that group, and these are 3 cycles. That means that their contribution to the cycle index of the group will be x3 to the 1st power, because I have 1 cycle of length 3. Now, the cycle index of the permutation group is defined by this, that I am summing up all the cycle types of all elements and dividing these by the order of group. So one can say that this is arithmetic mean of the cycle types. Now, if I am doing this for this group, then this coefficient is by dividing with the order of the group, and I have one permutation with this cycle type. I had 3 permutations with cycle type x1, x2, and I had 2 permutations with cycle type x3. So the cycle index of this group is this kind of polynomial expression, or polynomial with 3 variables. Okay, now I can also assign to each permutation in the permutation group a so-called character of a permutation, which will be simply defined as the number of fixed points in the permutation G. In other words, the number of one cycles in that permutation. So if I am returning back to the previous example, then this has character 3 because it has 3 fixed points. These 3 elements have character 1 because they contain 1 fixed element. Here it is the 3, here 2, here 1. And these 2 permutations contain no fixed points, so their character is equal to 0. And the next lemma will say that how to compute the number of orbits if we know the characters of each element in the permutation group. And this lemma is appears in many books under various names. So here I am using the name Cauchy-Frobenius-Bernstein. At some places it is just the Bernstein lemma and so on. And also this lemma is related to the Poyas enumeration theorem because it is considering a special group action on special set. So if you know this lemma, then it is just a step further to the Poyas enumeration theory. So the lemma says that if I sum up all the characters in the group, and I'm dividing it by the order of the group, I'm obtaining the number of orbits in that permutation group. And the proof is a very nice example for the double counting argument. I will try to, just a moment, I will try to at least write some picture which will help understanding. In the first step, let us create a bipartite graph whose one part of vertices will be formed by the group elements, and the second part of vertices will be formed by the elements from the ground set. And I will add an edge between, okay, it's precisely oppositely, and I am putting an edge between G and alpha precisely when alpha is fixed by the element G. Now, so this graph will be bipartite, and I can regard this graph, or I can view this graph from 2 points of view. If I am taking an element of the group, then clearly its valency, or its degree in usual graph theoretic sense, is the number of elements which are fixed by that group element. So in the sense of the previous definition, it is the character of that element. So the valency of a group element here in the bipartite graph is the number of the elements which are fixed by this group element. If I sum all these characters or all these degrees, I am obtaining the number of edges in this graph. On the other hand, what is the valency of the element alpha from the basic set? It is the number of elements from the group which are fixing this element, that is, it is joined to all elements from the stabilizer of this concrete element alpha. And if I am summing all these values through the ground set omega, then again I am obtaining the number of edges in this graph. Wow. Now I can put together a few knowledges. We already know that the elements which are from the same orbit have the property that the sizes of the stabilizers are the same. Moreover, we know that they are strongly similar, but at this moment it is not important. It is enough that they have the same number of elements. So if I am summing up the orders of the stabilizer on one orbit, so I am now just restricting myself to one orbit, then I am obtaining as each summoned G beta or G alpha, because they are the same. And how many times I am obtaining G alpha? I am obtaining exactly the number of times which is the number of elements in the orbit formed by alpha and its images. So if I am summing the valencies on one orbit, then I am obtaining by the orbit stabilizer lemma the order of the group. And if I am summing all these elements through all elements of the ground set, then of course I am obtaining on each orbit one G. So altogether I am obtaining the number of orbits times the order of G. So after that, it is easy to express T, and you are exactly obtaining what the lemma says. So in my eyes, this is a very nice example for the double counting technique. This is my favorite. Now let's see on a concrete example. To everybody, it is clear that if I am generating a group by this element, that this group will have two orbits. 1, 2, 3 will be one of the orbits, and second orbit will be 4, 5. But let's check the lemma on this example. So the identity has 5 fixed elements. G to the first power has no fixed elements, so the character is 0. G to the second power has 2 fixed elements, 4 and 5, and so on. Now 5 plus 2 plus 3 plus 2 is 12, divided by 6 is 2. So it is in accordance with our expectation. Okay, this was a very basic example, but it shows you that if you know the permutation groups and its action or the cycle structures of its element, then you can obtain many more information about the combinatorial objects which is related to that group and so on. Now, probably everybody knows what are isomorphic graphs, so probably I will skip this slide. It is just a bijection between vertices which preserve the adjacency. So to prove that two graphs are isomorphic, it is enough to provide two labelings that look at this and this, and you will see that the adjacency is the same. And to prove that two graphs are not isomorphic, usually it is enough to provide an invariant which should be preserved by isomorphisms, but the values of that invariants are different for the two graphs. For example, if one graph has GERT 5 and the second has GERT 4, then clearly those two graphs are not isomorphic. But it can happen that a lot of invariants are the same, but the graphs are not isomorphic. So, for example, if I will show you these two graphs and I will give you the task to figure out whether these two graphs are isomorphic or not, then it is hard to find any easy argument, because the valencies of all vertices are 3, the GERT is 4 in both cases. So maybe it is a better idea to try to find some labeling which will provide an isomorphism. And yes, if you will try this, then after a while you will find the labeling of one graph and the other graph, which will tells you that these graphs are really isomorphic. Okay, and why we are doing all this stuff is we are joining permutation groups with graph theory, usually using group automorphism groups of graphs. So by the group of automorphisms of a graph, we mean all the permutations of the vertices which preserve edges as sets. So just for completeness, I showed the definition of the group automorphisms. And if I have, I don't know, 20 minutes, I will try to show or solve some examples for automorphism groups. So
yeah, yes, we have enough time here, and all participants are with us, so please continue.
Okay, thank you. But I need to make some technical changes in my computers to, okay. So if you have the cycle of length 5, then one can ask what is the full group of automorphisms of this graph. It is clear to everybody that if I will send 1 to the position, to the original position of 2, and 2 to the original position of 3, and so on, then all the edges will be preserved. So I have an edge 1, 2, edge which has end vertices 2 and 3, 3 and 4, 4, 5, and so on. So this graph is obtained by applying permutation 1, 2, 3, 4 to my original picture, and so on. If I will make more rotations, so this permutation in very easy manner corresponds to rotations of symbols. So I can derive at least 4 permutations which will be automorphisms of my graph. But of course, some reflections also preserves the edges. For example, through this axis, which is to which the permutation 2, 5 and 3, 4 corresponds, also preserves the set of edges. So this is also automorphisms, and I can do the rotations with this first picture here. So I can obtain this picture from the original picture simply by applying the permutation, which 1, 4 is on the place. I interchange 1 and 2 and 3 and 5 and so on. I will obtain 5 more automorphisms. What will be the last one? Last one will be, I think, this. No. Here, number 3 is fixed, 1 and 5 are interchanged, and 2 and 4 are interchanged. So, in a very easy manner, I obtain 10 permutations, and the question is whether they are more or not. Now, clearly, I can do two things. That I have seen that vertex 1 can appear on 5 different places. So if I say that my full group automorphisms is G, then the orbit of 1 under this automorphism group has 5 elements, because I could map the vertex 1 to 5 places. Okay, I'm sorry, I will erase this one in order to have some place. And this means that the orbit of 1 is of length 5. Now one can ask, what is the size of the stabilizer of 1? The stabilizer of 1 can be obtained again as, for example, the orbit of element 2 in undergroup G1 times the group which fixes 1 and 2. Okay, if 1 is fixed, then I can map the vertex 2 just to the neighbors of 1. So either to this place or to this place. So in that manner, I am obtaining that if 1 is fixed, then 2 can be mapped just onto 2 different places. And after that, I am asking what is the order of the group which fixes 1 and 2 under this. But if I am fixing 1 and 2, then everything other is fixed in the graph, because after that the second neighbor of 1 should be fixed, and so on. I can continue. So by application twice the orbit stabilizer lemma, I am obtaining that that the full group of automorphisms is of order 10, because I had on one step this one from the orbit stabilizer lemma. So this means that the full group is of order 5 times the stabilizer, or order of the stabilizer of the element 1. And I prove that the stabilizer of 1 is of order 2. So altogether, this means that G is of order 10, and it is not hard to see that, in fact, the corresponding group of automorphisms is the dihedral group of degree 5 or order 10. So are there any questions? It was very naive example, but I can show you a more challenging example. So determine the full group of automorphisms of the cube. And in graph theoretic mean that now I am not regarding cube as a solid, but as a skeleton of a graph. So I will somehow denote the vertices. Now, it is clear that if I will choose the approach first, that what is the order of the full group of automorphisms, then, for example, I can count by the orbit stabilizer lemma that the length of the orbit which contains 1 and to multiply it by the stabilizer of the element 1. It is clear just by simple rotation, I can map the vertex 1 to any other place in the cube. So clearly, this is of length 8, because I can map it to any place. Now, the problem reduces to the question, what is the order of the stabilizer of the element 1? So I am leaving the vertex 1 on the place, and I can ask what is the order of this stabilizer. Now I can take, for example, the vertex 6 as the next one for consideration. So clearly, the order of the stabilizer G1 can be obtained as the length of the orbit which contains element 6 under this stabilizer times the order of the group which fixes 1 and 6. It is easy to see that this vertex 6, when 1 is fixed, can be mapped only to these 3 places. If you consider that you are mapping 6 here or 6 here, you can finish the labeling of the cube in such manner that you will really obtain an automorphism. So the vertex 6 can be mapped into 3 places under the stabilizer of 1. Now, that means the next question is, what if I fix the elements 1 and 6? And after that, one can see that 2 and 5 should be also fixed, but I can interchange 4 and 5, 4 and 3, and 7 and 8. And this will provide me an automorphism which fixes 1 and 6, but it maps 3 to 4. So the vertex 3 under this restriction can be mapped either to to the vertex 4 or to stay on the place. So again, another using of orbit stabilizer lemma will say me that I have to multiply all these things by 2. Now, and if I leave on the place vertices 1, 3, and 6, then I'm losing all the freedom. Everything is determined uniquely. So finally, I am finishing the job, and I am obtaining the full group of automorphisms of the cube is of order 48. Now, I am leaving you as a homework to prove that G is isomorphic to S4 direct product with S2. Okay, so are there any questions to this? Okay, so I can come back to the usual presentation. Yes. Okay, so there are more homeworks for you. Derive the cycle index of any cyclic group Cn and show that there are no subgroups of order 15, 45, and 35 in the symmetric group of degree 5, 6, and 7 respectively. So if you would like to train the previous techniques, then you can try them on these examples. And also you can take any interesting or nice graph and to derive what is its group of automorphisms. Now a few words about the used sources. When I was preparing this talk, I was using 5 sources. There is a book which contains some lectures of Misha Klein. When I was his postdoc student, then he was giving a course, and I wrote this course, and after that we were able to publish it as a book. Also from the same series of book, a nice book on permutation groups by Gareth Jones, and a book which is, I would say, a Bible of algebraic theory, is published by Gotsil and Royle. If you would like to do anything in algebraic graph theory, I think you have to start with this book and to see what's going on in this area. It is really a nice book. If you would like to focus on permutation groups and more deep knowledge, then I recommend you the book by Dixon and Mortimer. And I was using an unpublished book by Klein, Purcell, and Woldar, and you cannot find, unfortunately, this book published because it was not finished yet. So thank you for your attention, and I'm sorry that I needed so much time. My original goal was to finish in 1 hour, but yes, I was talking much. I'm sorry for that. Thank you for your attention.
Thank you very much for a very nice lecture. And actually 1.5 hours is exactly a usual standard lecture in Russia. So that is exactly standard lecture in Russia.